In 1964, scientists at NASA's Jet Propulsion Laboratory noted that there would be a rare alignment of 4 planets, Jupiter, Saturn, Uranus, and Neptune, in the late 1970s that would give an unprecedented opportunity for a single spacecraft to explore more than one planet. NASA engineers began advocating for a program to build spacecraft to take advantage of this alignment and look at our solar system's outer planets in what they called the Grand Tour. That program would eventually become the Voyager program. 2 extraordinary spacecraft that gave we Earthlings not only a better look at the outer planets of our solar system, but our first real look at what lay beyond. Well, Voyager 1 was the first of the pair to encounter one of those planets, going by Jupiter in 1979, and the first to enter interstellar space in 2012. Voyager 2 was actually the first of the probes to be launched, and was the first and to date only spacecraft to visit our solar system's 2 ice giants, Neptune and Uranus. The extraordinary odyssey of Voyager 2 is history that deserves to be remembered. The rare opportunity provided by the unique planetary alignment had to do with a then relatively new concept called gravity assist. NASA engineer Gary Flandreau, who holds the Bowling Chair of Excellence in Space Propulsion at the University of Tennessee Space Institute, explained in a 1966 paper in the journal Acta Astronautica. Contrary to popular belief, indirect ballistic trajectories involving close approach to one or more intermediate planets need not require longer flight duration than is characteristic of direct transfer orbits. In fact, significant reduction of both required flight time and launch energy results if efficient use is made of the energy which can be gained during a mid-course planetary encounter. Simply put, gravity assist uses gravity of a planetary body to help slingshot a spacecraft, giving it acceleration. The technique can be used to not just speed the spacecraft, but to allow methods of speed and direction change that do not require fuel, which is normally in short supply on a spacecraft that must carry all the fuel it needs for speeding up, slowing down, changing direction, or stabilizing the spacecraft. Assuming the craft has no ability to acquire more fuel, the mission must be carefully planned within the confines of the amount of fuel the spacecraft can carry, called the delta V budget. Delta V referring to the total energy needed for the spacecraft's change in velocity over the course of the mission. While the first theoretical papers discussing the concept were published in the 1920s and 30s, it wasn't until 1956 that Italian engineer Gaetano Crocco calculated a mission that would use multiple gravity assists, proposing a 1-year exploration trip: Earth, Mars, Venus, Earth. The method of gravity assist was used in 1959 by the Soviet Luna 3 spacecraft, the first to photograph the far side of the moon. The craft used the moon's gravity to change the direction of the spacecraft. But there's a significant limit to the use of gravity assist, and that is the planetary body or large mass whose gravity you intend to use has to be in the correct place in order to direct your spacecraft to where you want it to go. How often that occurs depends upon the mission. It might be years in between times when planets align in such a way that you can use them to help get your spacecraft from one particular spot to another, and the proposed NASA Grand Tour is a relatively extreme case. The particular alignment that will allow the use of gravity assist to the outer planets being proposed occurs just once every 175 years. The same opportunity will not occur again until the middle 22nd century. This gave NASA a limited window of opportunity to get their craft together. The original NASA proposal was released in August 1969. They suggested 2 missions, each visiting 3 planets, including Pluto, still considered to be a planet at the time. One spacecraft would visit Jupiter, Saturn, and Pluto, the other Jupiter, Uranus, and Neptune. They proposed using an entirely new spacecraft, tentatively called the Thermoelectric Outer Planets Spacecraft, or TOPS, being designed at the Jet Propulsion Laboratory. But the estimated cost was high, as much as $1 billion, and the program had to compete with the new Space Shuttle program. Congress balked at the cost, and the mission had to be scaled back. Instead of an entirely new spacecraft, the missions would use one derived from the Mariner program, 10 spacecraft that had been launched between 1962 and 1973 to investigate Mars, Venus, and Mercury. Instead of the Grand Tour, 2 spacecraft would visit 1 planet each. This reduced the estimated cost to a more palatable $360 million per probe. But NASA was using a bit of an accounting trip because NASA was designing these 2 spacecraft with a mission life that would allow them to complete the originally envisioned Grand Tour, but only advertising visiting 2 planets, Saturn and Jupiter, in order to reduce the estimated mission costs. In 1977, the program was renamed Voyager. The probes would visit Jupiter, which had already been visited by Pioneer 10 and 11, and Saturn, which had been visited by Pioneer 11. In addition, the mission would allow a flyby investigation of Saturn's largest moon, Titan. Voyager 1 would be optimized for a visit to Titan, although there was an alternative option to visit Pluto instead. Titan, after being photographed by Pioneer 11, seemed to be more interesting. The second spacecraft, Voyager 2, would have options. The spacecraft would fly by Jupiter and Saturn, but could then continue to Uranus and Neptune. However, if Voyager 1 had not completed its objectives in its exploration of Titan, Voyager 2 could instead be redirected for another investigation of that moon instead of visiting the two ice giants. The two identical spacecraft would use 3-axis stabilization and a central parabolic antenna for communication. Attitude control was provided by 16 hydrazine fuel thrusters, and electrical power was provided by radioisotope thermoelectric generators, or RTGs. RTGs convert the heat released by the decay of radioactive material to generate electricity. This particular RTG designed for the Voyager program was the multi-100-watt radioisotope thermoelectric generator, or MHW, RTG, which produced 157 watts of electrical power initially, and halving that every 87.7 years. The craft carried 11 scientific instruments, and each also included a gold-plated copper golden record, a phonograph record that includes sounds and images intended to portray the diversity of life on Earth, and that, the hope is, could be deciphered by any intelligent civilization that might encounter the craft. In all, the Voyager spacecraft weighed 1,704 pounds, or 105 kilograms. Because of their different trajectories, Voyager 2, using a longer circular trajectory aimed at the grand tour of the four giants, was launched before Voyager 1. Voyager 1 was optimized to visit Jupiter and Saturn and Titan. This plan allowed flexibility and redundancy. By launching Voyager 2 first, NASA had the option to redirect Voyager 1 to the Grand Tour if the first launch failed. And as Voyager 2 would not reach Saturn until 9 months after Voyager 1, there would be ample time to redirect Voyager 2 to Titan if Voyager 1 was not able to meet its mission objectives there. Voyager 2 was launched using a Titan III Centaur launch vehicle, a rocket that married the upper stage of a Centaur rocket to a Titan III rocket. The more than 1.3 million pound, or 637,000 kilogram rocket produced 5,339 kilonewtons of thrust. The spacecraft was launched from Space Launch Complex 41 in Cape Canaveral, Florida on August 20th, 1977, 2 weeks ahead of Voyager 1. Both launches were successful, but a near-fatal complication arose with Voyager 2 in April. The main radio receiver failed. The backup was functional, but a capacitor in it also failed. This meant that NASA had to communicate on a precise frequency, which was then affected by a number of factors. NASA engineers were forced to calculate the necessary frequency needed for each transmission to the probe. The ability to continue its mission was a testament both to the value of redundant systems and the ability of engineers to adapt to unexpected challenges. Voyager 2's close approach to Jupiter came in July 1979. Using its less circular trajectory, Voyager 1 had made its closest approach in January. While Voyager 1's closer approach to the planet allowed greater image resolution, it gave a relatively short window to the gas giant's moons, rings, and magnetic field. Voyager 2 did not fly as close to the planet, but its trajectory allowed a greater investigation of Jupiter's Jovian moons. The flyby also allowed a comparison of observations between the two probes, allowing scientists to, for example, confirm the eruption of volcanoes that had been observed by Voyager 1 on Jupiter's moon Io, the first time an active volcano was observed on a celestial body other than Earth. Voyager 2's closer observations of the moon Europa led to speculation that the moon is composed of water ice. Voyager 2 also identified 3 previously unknown moons of the system's largest planet. Voyager 1 flew by Saturn the following November, 1980. Its flyby of Titan met all its mission objectives, freeing Voyager 2 to continue with the Grand Tour. Voyager 2 started its encounter with Saturn in August 1981 and was able to use its antenna to take measurements of the planet's atmospheric pressure and density, as well as taking more photos of Saturn's moons. There was a brief issue with the probe's photography platform that endangered the rest of the mission, but NASA engineers were able to correct the problem. And while Voyager 1 headed off to deep space, Voyager 2 would be the first, and so far only, spacecraft to visit the Uranium system, with its closest approach occurring in January 1987, where it discovered 10 moons, 2 new rings, before heading to Neptune. At the time, because of Pluto's elliptical orbit, Neptune was the farthest known body in the solar system. Like Uranus, Voyager 2 is the only probe to have directly explored Neptune, where it confirmed 6 new moons and 4 previously unidentified rings. NASA explains that the planet was not quite what scientists expected. The planet itself was found to be more active than previously believed, with 680-mile or 1,100 km/h winds, Hydrogen was found to be the most common atmospheric element, although the abundant methane gave the planet its blue appearance. The close flyby of the planet allowed an understanding of the ice giant that could not be achieved using Earth-based observation. It was Voyager 2 that identified the large anticyclonic storm that makes up the planet's Great Dark Spot, called GDS 89, very similar to Jupiter's Red Spot and Saturn's Great White Spot. The encounter with Neptune was considered to be the end of Voyager's 2 original mission. NASA reported that through the end of the Neptune phase of the Voyager project, a total of $875 million had been expended for the construction, launch, and operations of both Voyager spacecraft. Of their mission to the outer planets, Arizona State University planetary scientist Jim Bell told Scientific American in 2015, "They were revolutionary. The Voyagers discovered many moons around the planets we never knew were there, and even the ones we knew were there were literally just points of light in telescopes before that. All of a sudden they changed to geologic objects, to worlds that had weather and volcanoes and tectonics. It was just night and day." And then, just like its sibling, Voyager 2 headed off into the vast unknown, and the mission was renamed the Voyager Interstellar Mission. The spacecraft passed through the heliopause, which marks the boundary between matter originating from the Sun and matter originating from the rest of the galaxy, thus putting Voyager 2 in interstellar space on November 5th, 2018, more than 6 years after its faster sibling did. A fact sheet provided by NASA's Jet Propulsion Laboratory explains, had the Voyager mission ended after the Jupiter and Saturn flybys alone, it still would have provided the material to rewrite astronomy textbooks. But having doubled their already ambitious itineraries, the Voyagers returned to Earth information over the years that has revolutionized the science of planetary astronomy, helping to resolve key questions while raising intriguing new ones about the origin and evolution of the planets in our solar system. After providing enormous amounts of information about the outer planets, both Voyager 1 and 2 continue to transmit data, giving new information and detecting some scientific surprises about the nature of the heliopause and interstellar space. As they travel, they encounter challenges, and the plutonium powering their batteries slowly decays. And as it does, various instruments are shut down, but Voyager 2 still has 5 scientific instruments operational, according to NASA. The two craft are moving in different directions, allowing them to collect data not just on interstellar space, but to compare data between the two locations. A 2019 edition of National Geographic quoted Princeton University postdoctoral researcher Jamie Rankin. "We have been interstellar travelers since Voyager 1 crossed. But now Voyager 2's cross is even more exciting because we can now compare two very different locations in the interstellar medium." A 2020 discovery of a new kind of solar electron burst prompted Iowa Today to proclaim, "More than 40 years since they were launched, the Voyager spacecraft are still making discoveries. The Voyager mission is now the longest running and most distant space mission in history." Last year, the only antenna on Earth, Australia's Deep Space Station 43, that is capable of communicating with Voyager 2, had to be taken down for renovation and repairs. While scientists could still receive data from Voyager 2, they could not send instructions for more than 8 months. But when the antenna was repaired enough to send instructions, after the longest pause in the program's history, Voyager 2 responded without incident, still soldiering on more than 44 years after being launched. Astronomy magazine noted in 2020 that both should be able to keep at least one scientific instrument running until 2025. And even after that, NASA expects to continue receiving engineering data from the probes until 2035, when they will exceed the range of the Deep Space Network antennas. The importance of the Voyager program is profound, both in terms of the science gained and in terms of the meaning of the accomplishment of sending an object made by humans so far from home. Thomas Zberchin, Associate Administrator for the Science Mission Directorate at NASA headquarters in Washington, D.C., said in a statement in August 2017, "I believe that few missions can ever match the achievements of the Voyager spacecraft during their 4 decades of exploration. They have educated us to the unknown wonders of the universe and truly inspired humanity to continue to explore our solar system and beyond." A 2017 edition of the magazine Futurism put it simply, "NASA's twin Voyager probes are the most important spacecraft ever launched." I hope you enjoyed this episode of the History Guide, short snippets of forgotten history. And if you did enjoy, feed the algorithm by making a comment or clicking that like button. If you have suggestions for future episodes, please send those to our suggestions email box. Check out our webpage at thehistoryguy.net, and of course we're on Facebook, Instagram, and Twitter. You can book a special message from the History Guy on Cameo, and check out our merchandise at teespring.com. And if you'd like more episodes of Forgotten History, all you need to do is subscribe.